In today's lesson on Cramer's rule, we're going to learn yet another way to solve a system of equations. But first, in order to do that, we need to become familiar with what a determinant is. Now, a determinant is a group of numbers surrounded by these vertical bars called similar to absolute value bars. Each determinant has a specific number associated with it. And how we find that is we take this diagonal here, a times d. So let me draw a diagonal line through that. We take a times d, and then we subtract this value of b times c. Notice how we take that diagonal times each other minus that diagonal times each other. So let's go ahead and look at an example of what that would look like if we had 4, 2, 6, and 8. In this case, we're going to take our first diagonal, 4 times 8, and we're going to subtract from that 2 times 6. We end up with 32 minus 12, which gives us a final answer, 20. So the value of that determinant is 20. Let's take a look at another one. What if we had -2, 0, 7, and -6? Again, we're going to take the product of this diagonal here, -2 times -6, and we're going to subtract the product of this diagonal, 0 times 7. So that the value of this determinant is -12 minus 0, or positive 12. Since -2 times -6 is positive 12, we get positive 12. Alright, so how does this tie into solving systems of equations? Well, let's consider we have these two general equations. We have ax plus by equals c, and we have dx plus ey equals f. And this has the solution x, y. Some point where those two lines cross is going to be located at x, y. Well, we can find that x value and that y value using determinants. X is going to be equal to the determinant of the c value, the f value, the b value, and the e value over the determinant of the a value, the b value, the d, and the e value. Your y value is going to be equal to the determinant of your a, your d, your c, and your f. That's going to be all over the determinant of your a, b, d, and e. Now this is a lot to remember. And just some general tricks that I use to remember it. I notice that the bottom determinants include the left half of the equations in the order that they're in. So notice the coefficients of the x's go here on both denominators, and the coefficients of the y's go here on both denominators, just how they're written in the problem. Then I remember that the right side of the equation is going to be on the outsides of the numerators. Notice how these two numbers get placed on the outsides. Then you're left with the inside values, and I remember that for the x you use the y coefficients, and for the y, you use the x coefficients. I know that's a lot to remember, but let's look at some examples to hopefully cement that in. Alright, so let's take a look at these two equations. 3x plus 4y equals negative 7, and 2x plus y equals negative 3. I've color-coded them so that when we put them into the determinants, you can kind of see where I'm putting what values. First of all, notice that y doesn't have a coefficient associated with it. Since there's only one y there, we can kind of assume this coefficient to be 1. Alright, so first we have our x value. It's going to equal a determinant over a determinant. We also have a y value that's going to equal a determinant over a determinant. I think that the denominators are easiest to place because you simply use these four numbers on the left side. So I'm going to put in 3, 2, 3, 2, and I'm going to put in 4, 1, 4, 1, just as they're written. Now for the top, remember on the outside, I put these right numbers. So I put negative 7, negative 3, negative 7, negative 3. And then in the middle, for the x, I'm going to use the y coefficients, and for the y, I'm going to use the x coefficients. And for x, I'm going to use the y coefficients. So now we can find the values of each of these determinants to get us our coordinate. Remember, so we have x equals, let's find the value of this determinant. We have negative 7 times 1. And then we're going to subtract 4 times negative 3. The value of the bottom determinant, we're going to take 3 times 1. And then subtract 4 times 2. So that's our x. For y, we're going to have 3 times negative 3. And we're going to subtract negative 7 times 2. For the bottom, we're going to have 3 times 1. And we're going to subtract 4 times 2. Alright, so I've moved those x and y coordinates to the top. So let's simplify. We have x equals negative 7 plus 7. Or I'm sorry, plus 12. 4 times 3 is 12. And that's over 3 minus 8. For y, we have 3 times negative 3, which is negative 9, plus 14 over 3 times 1, which is 3, minus 4 times 2, which is 8. Continue simplifying, we get negative 5 over, positive 5 over negative 5, because negative 7 plus 12 is 5, 3 minus 8 is negative 5. For y, we get positive 5 over negative 5. So then for x, we get negative 1. For y, we get also negative 1. So we have the point at negative 1, and that is our solution using Cramer's rule. Alright, so let's look at one more. Let's say the two sides of a parallelogram are contained in the lines 3x plus 2y equals 8, and also 4x minus 2y equals 20. We want to find the vertex of those two lines, where they cross. So using Cramer's rule, we know that the x-coordinate is going to equal the two determinants over top of one another, as well as the y-coordinate. Remember, on the denominators, we're going to put 3, 2, 4, negative 2. 3, 2, 4, negative 2. On the numerators, I'll put 820 and 820 on the outsides. On the insides, for the x, I'll put the y's, which is 2, negative 2. For the y's, I'll put the x coefficients, which are 3 and 4. Okay, so now our determinants, we have x is equal to 8 times negative 2 minus 20 times 2 all over 3 times negative 2 minus 2 times 4. For y, we have 3 times 20 minus 4 times 8 all over 3 times negative 2 minus 4 times 2. So continuing to simplify, we get x equals negative 16 minus 40 over negative 6 minus 8. For y, we get 60 minus 32 over negative 6 minus 8. So then simplifying down further, we get x equals negative 56 over negative 14. We get y equals 28 over negative 14. So then we end up with x being equal to 4, y being equal to negative 2. We find that that vertex occurs at the point 4, negative 2. Yet another example of solving a system of equations using Cramer's rule.